Hello friends, welcome to CEC Gurukul Live Lectures. Dear friends, today in this session we are once again going to talk on carbohydrates in detail. We have discussed about carbohydrates in our previous sessions. Today we are going to talk on structural representation of cyclic form of glucose. And for the discussion we have with us in our studios Dr. Aprajita Chauhan. Dr. Aprajita Chauhan is Associate Professor in Department of Chemistry, Sri Aurobindo College, University of Delhi. Dr. Aprajita Chauhan has authored numerous books, and through the live platform of CEC, she gives you number of examples, a useful content which always helps you out in understanding various topics in detail. Friends, if you have any question in mind while listening to us, feel free to talk to us through our toll-free number. Our number is 1800110430. Now, I would like to welcome our guest, Dr. Aprajita Chauhan, once again. Hello, ma'am.
Hello, Jitika. Hello, viewers. In my previous lecture, I had focused on the open chain structure of glucose and had also discussed in detail the Fischer proof for establishing the stereochemistry of glucose. In that, we had seen that when we talk of the open chain structure of glucose, I had shown, with the help of the reactions, that glucose is an aldohexose and it has 5 hydroxyl groups in it, in which 4 are secondary hydroxyl groups and 1 is a primary hydroxyl group. We had also established that the 6 carbon atoms are in a straight chain. In today's lecture, we shall be discussing another important aspect of aldohexoses and ketohexoses, that is the cyclic structure of aldohexoses and ketohexoses. And then we shall be discussing the representation of these cyclic structures in Haworth form and the Chair Conformation for aldohexoses. So before I proceed further, I would like to discuss the drawbacks of the open chain structure. So as I've said that in today's lecture I shall be discussing, we've already discussed the Fischer's projections for straight chain structures of glucose. Today we shall be discussing the closed chain structures or the ring structures, and then Haworth projection formulae for the ring structure and the chair conformations. So when we see the different forms in which glucose can be represented, it is the open chain form, which we've already discussed in my previous lecture. Today we shall be discussing the cyclic structure of glucose as to how is it formed, and then the representation of the cyclic structure in Haworth form, which is the planar representation of the cyclic structure, and then the chair conformation of glucose, which is the more realistic representation for glucose. So before proceeding with this, I would like to discuss the objections to open chain structure of glucose. The open chain structure of glucose as it was proposed by Bayer could not explain all the reactions of D-glucose. That is, glucose has an aldehyde group, yet it does not give a Schiff's test. Also, it does not react with sodium bisulfite and ammonia. And then what we find is that if we talk of glucose pentaacetate, it does not react with hydroxylamine, which indicates that glucose does not have a free aldehyde group. So what I have shown here is that glucose reacts with acetic anhydride, resulting in the formation of a cyclic glucose pentaacetate. So if it was an open chain structure, that is an aldehyde group was not involved in a ring, it would show a reducing property. That is, it would react with ammonium hydroxide. But what we find is that when we do the reaction of glucose with ammonium hydroxide, it does not react, which indicates that it does not have a free aldehyde group as indicated here, whereas it is in form of a cyclic structure. Not only this, As I've said, that glucose has a tendency, the open chain structure exists in a very small form, that also in solution, and it has a tendency to form a cyclic structure. And when we talk of a crystalline structure of glucose, what we are doing is we are talking of the cyclic structure, that is the hemiacetal structure. And in this case, D-glucose exists in two isomeric forms. One is the alpha D-glucose, whose melting point is 146 degrees and specific rotation is 112 degrees. And this can be obtained by crystallization from cold concentrated aqueous solution. Whereas if we talk of beta D-glucose, its melting point is 150 degrees Celsius, its specific rotation is 19.2, and it can be obtained by crystallization of glucose from hot saturated aqueous solution. This is only possible to get two isomers, that is the alpha D-glucose and the beta D-glucose, if the first chiral carbon is asymmetric. But if we talk of the open chain structure here, what we find is that this first carbon is not asymmetric, since in this case this carbon is attached to oxygen with a double bond. Not only this, the open chain structure could not explain the phenomena of mutarotation. Now, what is mutarotation? Mutarotation is a process in which the specific rotation of a particular compound changes on standing in solution with time until it attains a specific value. So this, when we took glucose, if we consider of the open chain structure of glucose, it was not able to explain the phenomena of mutarotation, that is the change in specific optical rotation of glucose on standing with time. Next, what we know is that when we talk of an aldehyde reacts with methanol in presence of HCl to form a hemiacetal, and if it reacts with excess of methanol, then it forms an acetal. But when we talk of glycosides or the hemiacetal of a glucose, then what we find is that glucose, being a hemiacetal molecule, it will give us two acetals. That is, it will give us alpha D and beta D methyl glycosides, which could not be explained on the basis of the open chain structure of glucose. For this, the condition necessary is that the first carbon should be asymmetric, and which we've already seen that this first carbon is not asymmetric in the open chain structure of glucose. So now we conclude from this that we can say that glucose exists in three different forms. One is the open chain form, which occurs in very small amount in solutions. And then we have two cyclic forms. One is the alpha D-glucose, that is this structure, and the other one is the beta D-glucose. Why is it that the open chain structure occurs in such a small amount in solutions? Because it has higher energy and is less stable than the cyclic counterparts. So what happens is that when we talk of the sugar or the glucose that we come across, which is the solid crystalline structure, it is in fact the cyclic structure. And this cyclic structure, when we dissolve in water, it undergoes ring opening and is converted to open chain glucose, open chain structure, which is the glucose, and which gives us the reactions of an aldehydic and a hydroxyl group. Now, the closed chain structure is more stable as compared to open chain structure, because the energy is less and hence it is more stable. So open chain structure has a tendency to form a cyclic hemiacetal. Now, and here what I've shown is, I have shown the Fischer's projection for the open chain glucose, and then this is the alpha D glucose, and this is the beta D glucose, which results due to cyclization of the open chain. We shall be very soon seeing how does this cyclization reaction take place and why does it take place. We know that an aldehyde reacts with one molecule of alcohol to form an hemiacetal, and if we take the alcohol in excess, then it reacts with two molecules of alcohol to form an acetal molecule. The open chain hemiacetals are not stable and they decompose spontaneously to give us back an aldehyde and alcohol. So what we find here is that when we talk of a reaction of an aldehyde with an alcohol, this is a nucleophilic addition reaction. That is, the lone pair of electrons on oxygen act as nucleophile, and as we've seen that in this carbonyl carbon, the carbon will have a partial positive charge and oxygen has a partial negative charge. Because of the difference in electronegativity of the carbon and the oxygen, so this oxygen acts as a nucleophile and attacks the electrophilic carbon, and this hydrogen, that is proton, forms a bond with this oxygen, resulting in the formation of a hemiacetal. So, but what we find in case of glucose and other aldohexoses and ketohexoses, that is when an aldohexose reacts with an alcohol, with an alcoholic group, it forms a hemiacetal and a ketone forms a hemiketal. How does it happen? Now what we find is that when we talk of a glucose molecule, then what we see is that glucose molecule has an aldehyde group, and then along with an aldehyde group, it has 5 hydroxyl groups. So one of the hydroxyl group reacts with the aldehyde, the carbonyl group, to form in an intramolecular reaction to form a cyclic hemiacetal. So what we find here is that this oxygen acts here as a nucleophile. It forms a bond with this carbon, resulting in this bond formation here, and this H forms a bond with this oxygen, resulting in the hemiacetal molecule. Next, what we find is that the carbonyl carbon, which was the first carbon in glucose, has been converted into a asymmetric carbon, and this carbon is known as the hemiacetal carbon. This I shall be discussing in detail when I deal with anomers. So what we find is, now let us look into this reaction. If we talk of a glucose molecule, then what we find is that glucose has 5 hydroxyl groups. Now the question arises, which of the hydroxyl group will react with the carbonyl, with the aldehyde group here. So we know from the stability of cycloalkanes, that is, the ring having 6-membered ring is the most stable conformation, or is the most stable ring, because it can occur in a puckered conformation, that is the Chair conformation. So this, if we do the reaction of this oxygen, that is this hydroxyl group which I have highlighted, then the lone pair of electrons on this oxygen form a bond with this carbon, resulting in a 6-membered ring, that is first 1, 2, 3, 4, 5 and 6. So this oxygen is forming the part of this ring. It results in a 6-membered ring. And then next what we find is, when initially we had a double bond between carbon and oxygen, so we know that the structure here is planar. So now when this oxygen makes a bond with this carbon, it can either attack this carbonyl carbon from the upper face or from the lower face, or I can say it can react from the right hand side or from the left hand side. I am talking of the right hand side and left hand side here because we are talking initially here as of the Fischer projections. So what we find is that we can have two configurations around the hemiacetal carbon. That is, the OH can be on the right hand side, and when OH is on the right hand side, we call it as the alpha form, and when the OH is on the right hand side in Fischer projection, then what we say is that this is the beta form. And here I have shown the Fischer projections for the cyclic forms of glucose. But in practice, what we do is we represent the cyclic forms in form of Haworth projection formulae. And what we find in Haworth projection formulae, that these cyclic rings, that the Haworth rings are represented in flat forms. But normally, please remember that these rings are not flat. And now we will represent these aldoses and ketoses either as 6-membered or 5-membered rings, including oxygen as one atom. So what we find is that most of the aldohexoses are represented in form of a 6-membered ring in which oxygen is the heteroatom. And if we talk of aldotetrosis, aldopentoses, ketohexoses, then what we find is they form 5-membered rings. And these rings, 6-membered rings, are known as pyranoses, and 5-membered rings are known as furanoses. This is because these are named because they have the analogy with, or they are analogous with the cyclic ethers, which is pyrene. Pyrene is a 6-membered cyclic ether in which oxygen is the heteroatom. And since the aldohexoses like glucose forms a 6-membered ring, we call it as pyranosis. Osis is indicating that it is a carbohydrate. And we will remember that furanosis is a 5-membered ring from the word, the first alphabet, that is furan. So that means now alpha D glucose is also called as alpha D glucopyranose, and ribose, which is a 5-membered ring, is called as alpha D ribofuranose. Now the alpha indicates the configuration of the OH at the hemiacetal carbon. So if the OH is on the lower side at the hemiacetal carbon, it is known as the alpha. So you can remember this alpha from the word, from alpha, that is, we can indicate that alpha looks something like a fish. So fishes are always at the bottom. So the alpha form is indicating that the OH is going to be on the bottom of the anomeric carbon, that is the hemiacetal carbon. And in furanose, so that means pyranose and furanose are indicating the number, the size of the ring. That is, a pyranose ring is a 6-membered ring and a furanose ring is a 5-membered ring, in analogy with the ethers, cyclic ethers, pyrene and furane. So now when I talk of a beta isomer, then what we'll mean is that the OH is on the top. So top you can remember, that is, it is flying. So it will be on the top, and flying means birds fly. So that means beta, if I talk of a beta isomer or the enomer, then the OH will be on the top. So this is the difference between the alpha and the beta forms. So now when we talk of glucose, then what we see that glucose can cyclize in two ways. The first is that the OH on the fifth carbon, that is the O of the OH group, which is attached to the fifth carbon, acts as a nucleophile and it makes the bond with this carbonyl carbon, and this proton goes to this oxygen here, resulting in the six-membered ring. The other alternative is that the OH on the fourth carbon reacts with the carbonyl group, resulting in the formation of the five-carbon ring. So for glucose can exist in two forms, that is the six-membered ring and the five-membered ring. But we know that the six-membered rings are more stable as compared to five-membered rings. For six-membered rings, we can also put them in the chair conformation. So hence, the pyranose form of glucose is more appropriate representation of glucose structure. So now when we talk of Haworth projection formulas in detail, so what you have to remember is that this solid bonds which I have shown here, these are the bonds which are coming towards the observer, the solid, this is showing the plane, and these are the groups which are above the plane, and these are the groups which are below the plane of the ring. So now when we talk of a Haworth projection, what you have to remember is Haworth projection is in this case we represent the six-membered ring as a flat ring, and in fact the six-membered ring is not a flat ring, but biologists use it in biology when they are representing the structure of a DNA, RNA or starch, or we talk of cellulose. Whereas when we talk of a chemist would definitely prefer to represent this six-membered ring in form of a chair, because chair is the more realistic representation of a cyclic structure having six carbons, because in that case we are able to show the puckered structure of the ring. So when we talk of the structure of Haworth projection, then what you have to remember is that in Haworth projection, ring oxygen is always placed in the back right hand corner of the ring with C1 on the right hand side. And then what we do is we put the primary hydroxyl group is attached to C5 and it is drawn up from the fifth carbon in the left hand corner if the molecule is having D configuration. And a result of this reaction between the OH on the fifth carbon and the carbonyl group, two hemiacetals are formed, and the carbonyl carbon of the open chain aldehyde becomes a new asymmetric center in the hemiacetal. And then what you have to remember is if the OH group bonded to the new asymmetric carbon is down, that is trans to the primary hydroxyl group at C5, then the hemiacetal is alpha D glucose, and if this OH is pointing up at the anomeric carbon, then the hemiacetal is beta D glucose. So now let me explain this with help of the structure. So what we mean here is that we are drawing the pyranose structure, and in pyranose structure you have to remember is that this oxygen is going to be always on the right hand corner on this side, and the first carbon, the carbonyl carbon, which was the carbonyl carbon in the open chain structure, becomes the anomeric carbon or the hemiacetal carbon, and it will be on the right hand side. Now since it is a D isomer, please remember this CH2OH has to be on the top attached to the fifth carbon. if it was the L configuration, then in this case CH2OH would be facing downside here. And now when we compare these two Haworth structures, what we find is that the configuration at the second carbon, third carbon, fourth carbon and the sixth carbon, it is the same. It is only at the configuration at the first carbon is different, and this first carbon becomes asymmetric as a result of cyclization, and in this case the OH is on the lower side. If the OH is trans to CH2OH, then in that case we say that the configuration is alpha, and in case the OH is on the same side of CH2OH, then we say that the configuration is beta. And if CH2OH is on the top, on the uppermost side, then in that case we say that the configuration of the sugar in the open chain structure was D configuration. So these are the Haworth structures. As I've said that chemists believe that we should represent the Chair conformation. Now we know that if I talk of a cyclic hydrocarbon, which is cyclohexane, then we know that cyclohexane are the most stable structures because they can exist as puckered structures, and since the carbon is tetrahedral, and in this structure we can represent all the atoms in tetrahedral form, so there is less of steric repulsion, and these can be expressed in two forms, that is the chair form and the boat form. So here I have shown one chair form, and then I have flipped the molecule, and this is the other conformation for the Mannose form. Now if that means, because now as I have already said that because of the tetrahedral, this carbon has a tetrahedral, this is sp3 hybridized, so that means the structure would be tetrahedral, and therefore it can exist the chair or the boat form. But the chair form is more stable, because what we find is there, if I go back to the boat form, here this angle, this distance between the axial bonds is less, and there is more of steric repulsion. Whereas if we talk of the chair form, then the bond length is more and it is free of steric repulsions. So before I proceed further, I would like to just make a quick, I'll recapitulate that this is the plane of the ring, and the bonds which are, and this is the axis of the ring which is perpendicular to the plane. So bonds which are perpendicular to the ring, this like this, or they are the axial bonds, and the bonds which are parallel, they are the equatorial bonds. And what you have to remember is that if the bulky groups are put on the equatorial position, then what we find is that they are pointing outwards, and there will be less of steric hindrance, and that form will be more stable. So if now I convert a Haworth projection into a chair conformation, then what you have to remember is that in chair conformation, the CH2OH is equatorial, and in chair conformation it is the only the anomeric OH which is axial. All other OH are equatorial in position. Whereas when we talk of the beta conformation, that is in the chair form, then what we find is that in this case the CH2OH group as well as the OH group is equatorial. So how do we distinguish between the chair conformation and the alpha form D, alpha D glucose and beta D glucose in chair conformation? We can say that in alpha D glucose, the anomeric OH, that is at axial position, whereas in beta form, the anomeric OH is at equatorial position. This is only where the configuration is different. That is, alpha form has OH below the plane, that is, it is trans to CH2OH. So you will remember this from fishes. Fishes stay down, and if I talk of beta, then you have to remember from beta. Beta means birds which stay high up in the sky, and therefore the OH is on the upper side, that is, this is the equatorial position. And at all other asymmetric carbons, the configuration is the same. So that means the cyclic form of glucose is only differing at configuration at carbon 1. In alpha form, the OH is pointing downwards, whereas in beta form, the OH is pointing upwards. Now we know that glucose is the most abundant or most prevalent aldohexose in nature. Why is it so? Because glucose is the most stable aldohexose. And why is it the most stable aldohexose? Because if we look into the structure of beta D glucose, then what we've seen that all the OH substituents, which are the bulky substituents, that is CH2OH is a bulky substituent which is at the 6th carbon, and all other OH are also bulky substituents. They are present at the equatorial positions. And since they are present at the equatorial positions, the electron-electron interaction, that is steric repulsion, is minimum. Hence the energy is least, and it is the most stable conformation. And the axial positions, as I have said, are occupied by hydrogens, which will occupy very less space, and hence they experience very less steric strain. And what we find is that no other aldohexose exists in such a strain-free conformation. So if I talk of ribose, then ribose is that is a aldopentose. It is occurring in a furanose structure, and we know furanose structure is a flat ring. So what we say is that glucose is the most stable conformation, or is the most stable aldohexose, and is hence most prevalent in nature. So now let us look into the mechanism of cyclic hemiacetal formation. So what happens in this case is the protonation of the carbonyl oxygen takes place. When the protonation of carbonyl oxygen takes place, what we find is that these electrons, the pi electrons, move towards oxygen, neutralizing the positive charge on it, and this oxygen acts, the lone pair of electrons on oxygen, which is present on the fifth carbon, 1, 2, 3, 4, fifth carbon, acts as a nucleophile and attacks the carbon. Now when this happens, what we find is that this can react either from this phase or from now the bond becomes single, so it can react either from either of the phases here, resulting in 2 anomeric forms. So we get this cyclic structure here, and in the next form what happens is deprotonation takes place, that this proton is removed by water, which is acting as a catalyst here. In this case it is acting here as a base because of the lone pair of electrons on oxygen, and removes these protons, resulting in the formation of a cyclic hemiacetal. So what you have to remember is that this oxygen is derived from the OH group, and this H is derived from the CHO group. If I can now, so this is how the cyclic hemiacetal is formed. So what you have to remember is, now if I simplify it, the structure, then what we can remember is that this O will form the bond with this carbon here, and this hydrogen is coming to this oxygen, resulting in the formation of hemiacetal. Now the question comes, how are we going to convert Fischer projection to a Haworth projection? So first, what are we going to do in this case? This is very important. We will convert the open chain structure into Fischer projections, and you have to remember that these are the bonds which are going away from the observer, and these are the bonds which are coming towards the observer. After drawing this structure, what we do is we rotate this bond by 90 degrees in clockwise direction. Please do not rotate it anti-clockwise direction, because then we will not get the correct Haworth manipulation. So what we do is we twist it or rotate it by 90 degrees. When we do this, what we find is that the groups which are on the right hand side of the carbon, they come down. So what you have to remember is that when we are making the Haworth structure, the bonds which are on the right are going to come down in the ring, whereas bonds which are on the left will point up. That means left is lifting, right is down. So now we will write it in such a form so that the bonds which are on the right hand side will come below, and bonds which are on the left hand side, the groups, will come up. Now next what we do is we have to now write the molecule in such a manner so that this CH2OH group coils back, and the OH which is on the fifth carbon comes in front of CHO, forming the part of the ring. So what we do for this is we've written in this form. Now since I have to bring this CH2OH back and I have to attach it to the fifth carbon, so what we do for this, we rotate the bond between the C4 and the C5. When we rotate the bond between the C4 and the C5, what we observe is that OH takes the place of CH2OH, as I have shown here. CH2OH takes the place of H, and H takes the place of OH. So this is what interchange we have done, and when we do this interchange, what we find is that now OH forms the part of the ring here, will form the part. This OH now acts as this lone pair of electrons on oxygen, which is attached to the fifth carbon, act as a nucleophile, and now we close the ring. As I have showed you earlier also, that first this will undergo protonation. This bond forms here, resulting in the formation of the cyclization of the ring here. So now what we find is that when we talk of a Haworth projection, if this C1, that means this carbon here, the carbonyl carbon here, which is the first carbon, this is the first carbon in this structure. This has now become asymmetric, and here we can have two possible configurations. That is, the OH can be on the top or it can be at the equatorial position. Then we say this is the beta isomer or the beta anomer, and if OH is at the bottom, then the isomer is the alpha anomer. And in this case, we can also identify the alpha and the beta forms by saying that in alpha form, CH2 and OH, CH2OH and the OH on the first carbon are trans to each other, that is the anomeric OH are trans to each other, whereas in beta form, the anomeric OH and CH2OH are on the same side of the ring, that is they are cis to each other. Similarly, what I have shown for ribose, that we write the structure in such a manner so that the CH2OH is on the left hand side, and when we are writing the D form, please remember this CH2OH has to be on the top. And second form, that when we are writing the furanase form, what you have to remember is that in furanase form, the O is going to be on the top of the ring, whereas in case of pyranose form, the O is going to be on the right hand side corner of the ring. So what we find here is that when we have done the cyclization, again we are getting two anomers. In one, the OH is on the opposite side of the CH2OH, that it is trans to OH, which is the alpha D ribose, that is OH is on the lower face, whereas in beta phase the CH2OH and the anomeric OH are on the same side, and this represents the two anomers. So what we find is, case of anomers, the configuration around the anomeric carbon or C1 is different. That is, the OH can be below the plane. If it is below the ring, then we say it is the alpha one, alpha anomer, and if it is above the ring, we say it is the beta anomer. So now if I talk of a shortcut method, that instead of drawing all the structures, what the easier way for drawing the pyranose structure for this is that first you draw a pyranose ring, that is without all these groups. And what you have to remember in pyranose ring, that the oxygen has to be on the right hand corner. Oxygen will always be here. Now this is the anomeric carbon, this is the first carbon, and this is the primary hydroxyl group. Now when we do this, please remember the second and the third carbon. This is the second and the third carbon, that is these two carbons. Here the configuration will not change. So what we find is that, please remember, now as I've said, the groups which are on the right will go down. So this, we do not talk of the anomeric carbon, but if I talk of this second carbon, the OH is on the lower side, it's on the right. Then H I have not shown here, H will be here. Again the OH will be on the right hand side, again it is on the lower side, and this OH becomes the oxygen here, and this CH2OH, since it is the D form, it will be written upwards. So what you have to remember now is that all those groups which are on the right hand side, they will go down, that is second, third, fourth, they will go down, these three. Fifth OH becomes the, from this fifth we get the O here, that is the pyranose oxygen, and this CH2OH will be attached to the fifth carbon facing upwards if it is the D sugar. If it was an L sugar, this would have come down. So what I have written here now, we've shown here is the alpha isomer, since OH is facing downwards. Now what you have to do is, I've given you a small exercise in which we have to draw the structure for mannose. So what you have to do is, as I've said, for drawing the structure of mannose, what you have to remember is you draw the pyranose ring. You remember that this fifth OH is becoming the O in the pyranose ring, and at this position we will have the CH2OH at top, since it is the D mannose. Now at the second and the third, the configuration is going to be the same. So that means at the second carbon here, now if I talk of mannose, OH is on the left hand side. Now since OH is on the left hand side, it will go up here. Again, second and third it is up, fourth it is down, fifth has formed the oxygen which is acting here as a nucleophile and is making the bond with the first carbon, and this OH at the anomeric carbon is down. So that means this is the alpha configuration for D mannose, and we name it as alpha D mannopyranose. Similarly, if I have to draw the structure for the galactose, then what you have to remember is, now this we are discussing in long way, that for galactose we will rotate the ring in right hand direction, so that all the groups which are on the right hand side will come below the ring, and one which are on the right hand side will come below the ring, and which are on the left hand side will be above the ring. Now we will twist this bond, that is C4 and C5, so that OH faces this carbon, and now this O can form a bond with this carbon either from the top or from the bottom, since this group is planar, resulting, and then we will now close the ring from this oxygen, and this hydrogen, we can say this hydrogen will make a bond with this oxygen here, and this oxygen will make a bond with this carbon, and we will close the ring, resulting in the formation of the pyranose. And when we talk of galactopyranose, then what we find is that again we can have two anomers, that is the OH can be, here we have represented it like this with a broken line, so that this OH can be either on the top, which will be the beta isomer, or it can be at the bottom, in which case it will be the alpha isomer. Now when we talk of a hemiacetal structure for fructose, then we know that fructose is a ketohexose, and in this case hemiketal structure forms as a result. I am sorry, here there is a misprint, it should not be hemiacetal, it should be a hemiketal structure, and a hemiketal structure forms due to reaction between the OH on the fifth carbon and the ketonic group which is at the second carbon, resulting in a 5-membered ring, which is the furanose ring. So what we find here is that, and next you have to remember is, now when I look into the structure, this structure of fructose, then what we find is that in this case this is the beta form, because in this the OH and CH2OH are on the same side of the ring, so they are cis to each other. Again the mechanism is the same as we did for glucose for the closing of the ring, that is, first we rotate the ring in such a manner so that the OH on the fifth carbon is facing the carbonyl group, and then we close the ring by making a bond between this oxygen and carbon here, and if resulting in the cyclic form. So if I look into the mechanism quickly, then what we find is that this H plus reacts with the lone pair of electrons on oxygen in acid-base reaction, increasing the electrophilicity of the carbonyl carbon, and this O acts as a nucleophile, resulting in this structure. And in the last step, then the water molecule, that is the lone pair of electrons on oxygen acting as a base, abstract a proton from here, resulting in the cyclic Haworth structure for fructose. Now let us look into what do I mean by anomers of monosaccharides. I have been using this term again and again. So when a pyranose or a furanose ring is formed, we've already seen that the carbonyl carbon is converted into an asymmetric carbon in an hemiacetal structure. Now when the hemiacetal OH group can now be either directed up or can be directed down. If it is directing up, that is, we say then it is the two orientations of the OH groups in hemiacetal gives rise to diastereomers, which are known as anomers, and the hemiacetal carbon is the anomeric carbon. Now when I talk of anomers, so alpha D-glucose and beta D-glucose are anomers, that is, they are differing at the configuration at the anomeric carbon. This, whether the OH will be on the top side or on the bottom, will depend as to on which face the oxygen is attacking. Then the second point that you have to keep in mind is that these anomers are diastereomers. That is, their properties will be different, as I've already said, that the melting point of beta D-glucose is 150 degrees, whereas of that of alpha D-glucose is 146 degrees, and then the value for the optical rotation is also different. Now the question arises, how do we differentiate the anomeric carbon from rest of the carbons? So what we find is that the anomeric carbon is the only carbon which is attached to two oxygens. That is, this carbon is attached to an oxygen here, and it is attached to the OH of the attached to the oxygen of the hydroxyl group. And similarly, what we find in alpha also, that this anomeric carbon is attached to oxygen, ring oxygen, and then the oxygen of the hydroxyl group. Now please remember, these anomers are not enantiomers. What are enantiomers? Enantiomers are non-superimposable mirror images of each other, whereas when we talk of alpha D-glucose or beta D-glucose, they are not mirror images of each other, hence they are diastereomers. So this was the Haworth projection. Now when we talk of the chair form, chair conformation, then what we find is, in chair conformation, in the chair conformation of beta D-glucose, OH is present at equatorial position, whereas in case of alpha, it is present at the axial position here. Now there is little ambiguity. Now this method which we've been using, that the OH is at the axial position in alpha anomer, and OH is at the equatorial position in the beta sugar in the chair conformation, has a little shortcoming. What we find in chair conformation of alpha form, that an anomeric carbon has axial hydrogen while beta form has equatorial hydrogen. This method works only when chair conformation is drawn so that the anomeric carbon is at the right hand side. Right, this only works when this is at the right hand side. That is what I am trying to say, is that in chair conformation, when we talk of the alpha form, the OH, anomeric OH, is at the axial form. But now supposing I flip the molecule, then what we find is this axial hydrogen becomes a equatorial hydrogen. So hence we cannot, at the anomeric carbon, hence we cannot say this, it is always at the axial position. Similarly, if I talk of the beta conformation, then what we find is that in beta conformation also the equatorial will become the axial. So what is the better method to assign alpha and beta isomers in chair conformation? So what we say is, as long as the primary OH, that is this OH, and the anomeric OH are on the opposite side of the ring, that is, they are trans to each other, that means it is the alpha form. So what we find is, if we are writing it on the right hand side, the first carbon is on the right hand side, then what we find is that these two are on the opposite side. Now we flip the ring, and after we flip the ring, again what we find here is that these two groups, that is the primary hydroxyl group at the 6th carbon and the OH at the anomeric carbon, are on the opposite side of the ring, hence it is again the alpha form. Whereas in beta form, the OH will be on the same side. So what we find here is that in this case, the CH2OH on the 5th carbon and the OH, anomeric OH, are on the same side, When we flip the ring, we find that again in this case, both are at the equatorial position. Now, as long as we keep on following the rules, we can easily transform Fischer projection to Haworth projection and Haworth projection to Chair conformation. So what you have to remember is, while we are doing this, we will discuss the examples in the next lecture, but today I'll just tell you that groups which are on the right hand side on the Fischer projection will go down in the Haworth projection when we've done the pyranose structure. And in case of chair form, if we are talking of the now if we talk of the configuration, then what you have to remember is that in configuration, the group which is at the lower end at the anomeric carbon will have the alpha configuration, whereas groups which are on the left in Fischer projection, they will go up in the Haworth projection. And then what you have to remember is, if the OH on the anomeric carbon should also be up, then we'll say that it is the beta configuration. And then when we are converting it, this configuration, the beta configuration into chair conformation, what you have to remember is that the anomeric OH has to be at the equatorial position. We shall be discussing these few examples in my next lecture. I hope this has been useful, and you should be able to convert Fischer into Haworth and Haworth into chair conformation readily. Thank you.
A session on carbohydrates where we discussed about the structural representation, and friends, we believe that you might have gathered lots and lots of information, and this information is useful to you. We have this belief. Friends, if you have any question in mind, and if you feel so that your question to be answered, then feel free to write to us at info.cec@nic.in. We will try to give answers to your questions when next time Dr. Aparajita Chauhan will visit our studio, as well as you can give your feedback for this particular lecture too. We are taking your leave with the promise that we are going to meet again soon. Keep watching us through our YouTube channel too. Thank you for watching CEC Gurukul Live Lectures. Thank you, ma'am.
Thank you so much.